Welcome to this video. We're going to be talking about direct proof, and this is aligned with Mathematics Analysis and Approaches Standard 1.6. So what is a proof? In mathematics, if we make a claim about something, we can verify that claim through a series of logical steps, and we call that a proof. So take, for example, the pattern below. You see we are adding odd numbers in consecutive odd numbers in order. So 1 and then 1 plus 3, 1 plus 3 plus 5, so on and so on. Let's see what these equal. So obviously 1 equals 1, 1 plus 3 equals 4, 1 plus 3 plus 5 equals 9, then 16 and 25. Now if you notice, 1, 4, 9, 16, 25 are actually perfect squares, which we can rewrite as 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. So that leads us to the question, what can we conjecture? Well, adding up consecutive odd numbers, we conjecture, equals a perfect square. So we want to prove that the sum of n consecutive odd numbers is equal to n squared. So first we're going to write the sequence in general. 1 plus 3 plus 5 plus 7 plus so on and so on, however many consecutive odd numbers you're adding. So we know that this is actually an arithmetic sequence, and you'll notice between each term is just 2. So your first term is 1, and your common difference is 2. So we remember back to arithmetic sequences, and that the sum of an arithmetic sequence is given by this formula. So we can plug in the values that we know and solve for the sum. So this would be the sum equals n divided by 2 times 2, u1 is 1, so 2 times 1 is 2, plus n minus 1, and then d is 2. Simplifying further, we see that this is equal to n over 2 times this distributes out, and we get 2 plus 2n minus 2. Well, 2 and minus 2 cancel, so that leaves n over 2 times 2n, which is just n squared. So therefore, we can conclude the sum of consecutive odd numbers is equivalent to n squared, where there's n odd numbers. And that is our proof, our direct proof using logical steps. So there's some important vocabulary that you need to know when writing proofs. First one is conjecture. Now conjecture is when we notice a pattern and we make a statement about that pattern. We believe it to be true, but we don't have a proof for it yet. So that's called a conjecture. A theorem is when we have proved our conjecture. So it's an important true statement that has been proven. You also need to know these symbols. They will show up a lot. Z stands for integers, and integers are just whole numbers. And if it doesn't have a little plus sign, then we're talking about positive or negative integers. If it has a plus sign, we're just talking about the positive integers. If you see a Q, that's a set of rational numbers, so numbers that can be written as a fraction. And keep in mind, any integer, like 3, can be written as a fraction, so all the integers are included in the set of rational numbers. But it also includes fractions like 1/2, -3/4, and decimals that terminate, like 5.21. The last set you need to know about is R, or the set of real numbers, which includes the rational numbers, the integers, and the numbers that are called irrational numbers, like pi, which actually cannot be written as a fraction. So pi, there's no two integers, p divided by q, that equal pi perfectly. So you can think of it like a series of concentric circles. On the inside, you've got your integers, and the integer is contained within the rational numbers, which is contained within the real numbers, which is actually contained within the complex numbers as well. We're not going to talk about complex numbers in this lesson. So there are two important techniques that we're going to use when writing direct proofs. So the first technique is called left-hand side equals right-hand side proof. So pretty much when you solve left-hand side equals right-hand side proof, you're going to do some algebraic manipulation onto one side of the equation to show that it's actually equivalent to the other. However, keep in mind you can't start off with two equations equal. That would be assuming that you've already proved it. So you got to start with just the left-hand side and show it equals the right-hand side. The second thing we're going to deal with are even and odd number proofs. So keep in mind that an even number can be represented as 2k, where k is any integer. So think about like -4. That's equivalent to just 2 times negative 2, or 6, that's equivalent to 2 times 3. So we know a number is even if it's 2 times some integer. And then an odd number can be represented as 2k plus 1. So it's just one more than the even number. So where again, k is just any integer. So think about 5. 5 is equivalent to 2 times 2 plus 1. So in this case, your k would be 2. All right, let's try an example. Show that the sum of an odd and even positive integer is always odd. Okay, so let's start with any integer that's positive, and we'll call it m. And we'll say because it's odd that it's going to equal 2k plus 1. Now I'm going to write k1 is in the set of positive integers. Now this symbol right here that looks like a backwards e just means k1 is contained within z plus. In other words, k is a positive integer. Now I can do the same thing for an even number, and I'll call it n. So I'm going to say n equals 2k2. And I did k2 because I don't want it to be the same number as k1. And again, k2 is like k1, a positive integer. Now, I'm asked to find the sum and show that it's always odd. So I want to add m and m and come to the conclusion where I get 2 times some integer plus 1. That's how I know it will be odd. So let's do it. m plus n by what I wrote is equivalent to 2k1 plus 1 plus 2k2. Now if I regroup this, this is equal to 2 times k1 plus k2 plus 1. Well, notice that this, no matter what those integers are, is still going to be an integer. So I'm going to say k3 equals k1 plus k2, and k3 is also a positive integer. That leads me to m plus n equals 2 times k3 plus 1. Well, that means that m plus n must be odd. So that's my proof. Okay, this example is going to be a left-hand side, right-hand side proof. So we're going to simplify the left-hand side, simplify the right-hand side separately, and show that those two things equal the same thing. So let's start with the left-hand side. So left-hand side, I'm going to write LHS equals n plus 4 squared minus 3n minus 4. So n plus 4 squared is n squared plus 8n plus 16. And then again, that's minus 3n minus 4. So I can simplify this to get n squared plus 5n plus 12. Okay, now I'm going to do the same thing with the right-hand side. Keep in mind, I don't set these equal to each other from the beginning, because that would be assuming what you're trying to prove. N plus 1 times n plus 4 plus 8. So foiling, you get n squared plus 5n plus 4. And then you've got plus 8 as well. Simplifying, you get n squared plus 5n plus 12. As you can see right away, the left-hand side equals the right-hand side, so we write left-hand side equals right-hand side, and our proof is done. Alright, this last one we're going to try is another left-hand side, right-hand side proof, but it involves a little bit of tricky manipulation. So we have to remember the sum of a geometric series. So given a geometric series from r equals 0 to n of our first term times r to the n, we remember that this is actually equivalent to u1 over 1 minus r. And this, of course, is if r is less than the absolute value of r is less than 1. So in this case, we've got 1/2 minus 1/4 plus 1/4 minus 1/16, so on and so on. And we're told it equals 2/3. So we need to prove that this is true. And it's not going to be easily seen in this form. So let's actually regroup the terms. Here I'm going to write just the positive terms, 1/2, 1/4, 1/8, so on and so on, minus, and then the negative terms, 1/4, 1/16, and 1/64, and continuing on. So now you can see that these are actually two geometric series. So the first one is going to be a series from r equals 0 to n. My first term here is going to be 1/2, and then my ratio is also 1/2. That's going to be minus the geometric series from 0 to n of 1/4, my first term, and then 1/4 also my ratio. So now I can use the formula for the sum of an infinite geometric series and actually solve this out. So this is going to equal 1/2 divided by 1 minus 1/2, because 1/2 is my ratio and my first term. Similarly for the other one, 1/4 divided by 1 minus 1/4. So this is going to equal 1 minus 1/2 is equal to 1/2. 1 minus 1/4 is equal to 3/4. 1/2 divided by 1/2 is 1. So this first term is equal to 1. 1/4 divided by 3/4 is actually 1/3. 1 minus 1/3 is 2/3. So I've proven that the left-hand side equals the right-hand side, and my proof is done. All right, and that's it. So go ahead now and try some practice on your own.